Measuring EMF fields involves using a Gauss meter to measure the magnetic field strength in milligauss. Place the meter at different locations in the building, especially near suspected EMF sources, such as heating cables. Note the readings and identify areas with elevated EMF levels. For EMF mitigation solutions, firstly, grounding is important. Connect the heating cables and other electrical conductors to a proper grounding system to reduce stray currents in the EMF. Secondly, magnetic shielding can be used. Utilize magnetic shielding materials like mu metal or superalloy to block or absorb EMF. Place shielding around televisions, computers, and other sensitive equipment. Thirdly, rewiring is an option. Consider rewiring the heating system using shielded cables or separating the cables into smaller zones to reduce EMF. Fourthly, a Faraday cage can be implemented. Create a Faraday cage around the building or affected areas by covering the walls and ceiling with conductive materials such as aluminum foil or metal mesh. This will shield the interior space from external EMF sources. Regarding placing thin steel under a television, yes, placing a thin steel plate under a television and grounding it can help reduce EMF exposure. However, its effectiveness depends on the strength and frequency of the EMF field. Monitor the EMF levels before and after grounding the plate to assess its impact. Other considerations include building code requirements. Verify if there are any specific building code requirements regarding EMF levels or mitigation measures. In terms of health effects, while the World Health Organization classifies EMF as a possible carcinogen, the exact health effects at lower exposure levels are still being studied. Consider consulting with an experienced electrical engineer or electromagnetic compatibility expert to provide a comprehensive assessment and mitigation plan. A Gauss meter is an instrument used for measuring the strength of a magnetic field. It can measure both the magnitude and, in some models, the direction of the magnetic field. The unit of measurement for magnetic field strength is typically milligauss. When using a Gauss meter, it's important to calibrate the instrument according to the manufacturer's instructions to ensure accurate readings. Position the meter at various points of interest, holding it steady and away from any personal metallic objects or other potential sources of interference. Take multiple readings at each location to get a reliable average. Note the distance from the EMF source when taking measurements, as the magnetic field strength decreases with distance. When evaluating EMF levels, consider the applicable standards or guidelines provided by regulatory agencies or health organizations. Grounding is a critical safety measure in electrical systems designed to provide a low impedance path for fault currents to return to the source. A properly grounded system helps prevent electrical shock hazards and minimizes the risk of fire. To implement grounding, connect all non-current carrying metal parts of electrical equipment to a grounding electrode, such as a ground rod or grounding grid. Ensure that the grounding conductor is of adequate size to safely carry the maximum fault current. Regularly inspect and test the grounding system to verify its integrity and effectiveness. Magnetic shielding involves using materials with high permeability to redirect or absorb magnetic fields, reducing their strength in a specific area. Mu metal and superalloy are examples of such materials known for their high permeability and effectiveness in shielding against low-frequency magnetic fields. These materials can be formed into enclosures, sheets, or wraps to surround sensitive equipment or areas. The effectiveness of magnetic shielding depends on the material's permeability, thickness, and the geometry of the shield. Ensure that the shielding material is properly grounded to provide a path for any induced currents. Rewiring the heating system may involve replacing existing cables with shielded cables or dividing the system into smaller, more manageable zones. Shielded cables have a conductive layer, typically a braid or foil, that surrounds the inner conductors and is connected to ground. This shield helps to contain EMF emissions from the cable. Separating the heating system into smaller zones can reduce the overall EMF levels by reducing the current flowing in each zone. This can be achieved by installing multiple smaller heating cables instead of one large continuous cable. Ensure that all wiring work is performed by a qualified electrician in accordance with applicable electrical codes. A Faraday cage is an enclosure made of conductive material that blocks electromagnetic fields. When an external electromagnetic field encounters a Faraday cage, it causes the charges within the cage's conductive material to redistribute, cancelling the field inside the cage. To create an effective Faraday cage, ensure that the conductive material completely encloses the area you want to shield. Any openings in the cage should be smaller than the wavelength of the electromagnetic radiation you are trying to block. The conductive material should be properly grounded to provide a path for any induced currents. Materials such as aluminum foil, copper mesh, or steel sheets can be used to construct a Faraday cage. The effectiveness of a Faraday cage depends on the conductivity of the material, the size and shape of the enclosure, and the frequency of the electromagnetic field. The effectiveness of placing a thin steel plate under a television and grounding it depends on several factors, including the frequency and strength of the EMF field, the size and thickness of the steel plate, and the quality of the grounding connection. The steel plate acts as a partial shield, redirecting or absorbing some of the EMF. Grounding the plate provides a path for any induced currents to flow to ground, further reducing EMF exposure. To assess the impact, measure the EMF levels before and after installing the steel plate using a Gauss meter. Compare the readings to determine the reduction in EMF levels. Ensure that the steel plate is properly grounded to a known good ground point. Building codes and regulations vary by location and may include specific requirements for EMF levels or mitigation measures in buildings. Consult with local building officials or an electrical inspector to determine if there are any applicable codes or regulations. These codes may specify maximum allowable EMF levels in certain areas of the building or require the implementation of specific mitigation measures. Ensure that the electrical system complies with all applicable codes and regulations. The World Health Organization classifies EMF as a possible carcinogen based on limited evidence from studies on humans and animals. The International Agency for Research on Cancer has classified extremely low-frequency magnetic fields as possibly carcinogenic to humans. However, the evidence is not conclusive, and the exact health effects of low-level EMF exposure are still being studied. It's important to stay informed about the latest scientific research and guidelines on EMF exposure. Expert consultation with an experienced electrical engineer or electromagnetic compatibility expert can provide a comprehensive assessment of the EMF issues in the building and develop a tailored mitigation plan. An expert can conduct detailed EMF measurements, identify the sources of EMF, and recommend appropriate mitigation measures. They can also ensure that all electrical work complies with applicable codes and regulations. The expert should have experience in designing and implementing EMF mitigation solutions in similar buildings. When measuring EMF, it's important to understand the different types of fields that can be present. Electric fields are produced by voltage, while magnetic fields are produced by current. The strength of an electric field is measured in volts per meter, while the strength of a magnetic field is measured in Tesla or Gauss. Most common EMF measurement devices, like Gauss meters, measure magnetic fields. When assessing EMF levels, it's important to consider both the magnitude and the frequency of the fields. Different frequencies can have different effects on the human body. The International Commission on Non-Ionizing Radiation Protection provides guidelines for limiting exposure to EMF at different frequencies. When selecting a Gauss meter, choose one that is appropriate for the frequency range of the EMF you're measuring. Some meters are designed for low-frequency measurements, while others are designed for high-frequency measurements. Ensure that the meter has sufficient sensitivity to detect the levels of EMF you are interested in. Consider factors such as the meter's accuracy, resolution, and ease of use. Calibration of the Gauss meter is crucial for ensuring accurate measurements. Follow the manufacturer's instructions for calibrating the meter. It's recommended to calibrate the meter regularly, especially if it is used frequently or if it has been subjected to extreme temperatures or humidity. When taking EMF measurements, be aware of potential sources of interference, such as nearby electrical equipment, metal objects, and personal electronic devices. These sources can distort the EMF field and affect the accuracy of the measurements. Keep a safe distance from these sources when taking measurements. Take multiple measurements at each location and average the results to reduce the impact of random variations in the EMF field. Record the date, time, and location of each measurement, as well as any relevant environmental conditions. This information can be helpful for analyzing the data and identifying trends. When interpreting EMF measurements, compare the readings to applicable standards or guidelines. These standards may specify maximum allowable EMF levels for different areas or activities. If the EMF levels exceed the applicable standards, take steps to mitigate the exposure. Mitigation measures may include shielding, grounding, or relocating the source of the EMF. When implementing mitigation measures, monitor the EMF levels to ensure that the measures are effective. Make adjustments to the mitigation measures as needed to achieve the desired reduction in EMF exposure. Keep records of all mitigation measures that are implemented, as well as the results of the monitoring. This information can be helpful for future reference and for demonstrating compliance with applicable regulations. When working with electrical systems, always follow safe work practices. Energize the equipment before working on it whenever possible. Use appropriate personal protective equipment, such as gloves and eye protection. Be aware of the potential hazards associated with electricity, such as shock and arc flash. If you are not qualified to work on electrical systems, hire a qualified electrician. When designing or modifying electrical systems, consider the potential for EMF emissions. Use shielded cables and equipment whenever possible. Separate electrical cables from sensitive equipment. Ground all metal parts of the electrical system. Minimize the length of electrical conductors. Use twisted pair wiring. Install filters on electrical circuits. When evaluating the EMF levels in a building, consider the cumulative effect of all sources of EMF. Even if individual sources of EMF are below the applicable standards, the cumulative effect may exceed the standards. Take steps to mitigate the cumulative effect of all sources of EMF. Consider the use of low EMF appliances and equipment. These appliances and equipment are designed to minimize EMF emissions. Look for products that are certified by independent organizations to meet low EMF standards. Educate occupants of the building about EMF and how to minimize their exposure. Provide information about the sources of EMF in the building, the potential health effects of EMF exposure, and the steps they can take to reduce their exposure. Encourage occupants to use low EMF appliances and equipment to keep a safe distance from EMF sources and to spend time outdoors. Regularly review and update the EMF mitigation plan for the building. As new technologies are developed and new information about EMF becomes available, the mitigation plan may need to be revised. Keep abreast of the latest scientific research and guidelines on EMF exposure. Consult with experts as needed to ensure that the mitigation plan is effective and up to date. The electric heating system uses continuous cables drawing 50 amps at 600 volts, which may produce elevated EMF levels. The use of SCR controls can introduce harmonics which may increase EMF. Understanding the characteristics of the heating system is important for determining the best mitigation strategies. When assessing EMF, it is important to understand the frequency and wavelength. The relationship between frequency, wavelength, and the speed of light is described with the equation C equals F multiplied by lambda, where C is the speed of light, F is the frequency, and lambda is the wavelength. Different materials can be used for shielding, depending on the frequency of the EMF. For example, mu metal is effective for low-frequency magnetic fields, while copper is effective for high-frequency electromagnetic fields. The thickness of the shielding material is also important. Thicker materials generally provide better shielding. The effectiveness of shielding can be improved by layering different materials. For example, a layer of mu metal can be used to shield against low-frequency magnetic fields, followed by a layer of copper to shield against high-frequency electromagnetic fields. Grounding is an important part of any shielding system. Grounding provides a path for unwanted currents to flow to ground, reducing the amount of EMF that is radiated into the environment. The grounding conductor should be as short and direct as possible. The grounding conductor should be connected to a good earth ground. A good earth ground is one that has a low resistance to ground. The resistance to ground should be less than 5 ohms. The effectiveness of grounding can be improved by using multiple ground rods. The ground rods should be spaced at least 6 feet apart. The ground rod should be driven into the ground as deep as possible. The effectiveness of grounding can be tested by measuring the resistance to ground. The resistance to ground should be measured using a ground resistance meter. A Faraday cage is an enclosure made of conductive material that is used to block electromagnetic fields. The effectiveness of a Faraday cage depends on the conductivity of the material, the size and shape of the enclosure, and the frequency of the electromagnetic field. A Faraday cage can be made from a variety of materials, including copper, aluminum, and steel. The material should be chosen based on the frequency of the electromagnetic field that needs to be blocked. The size and shape of the Faraday cage should be chosen based on the size and shape of the equipment that needs to be shielded. The Faraday cage should be properly grounded to ensure that it is effective. The heating cables are unusual in that they are continuous over an entire floor plate of the building. This configuration may make it more difficult to mitigate EMF than if the cables were zoned for each suite. Separating the cables into smaller zones can reduce the overall EMF levels. This can be achieved by installing multiple smaller heating cables instead of one large continuous cable. The smaller heating cables can be controlled by separate thermostats. This allows for more precise control of the heating system. This can also reduce the amount of energy that is used by the heating system. The use of SER controls on the heating cables can introduce harmonics. Harmonics are unwanted frequencies that can cause a variety of problems, including increased EMF. Harmonics can be reduced by using filters. Filters are devices that are designed to block certain frequencies. Filters can be installed on the electrical circuits that supply power to the heating cables. Filters can also be installed on the heating cables themselves. The effectiveness of filters can be improved by using multiple filters. The filters should be spaced at intervals along the electrical circuits or heating cables. Consider working with the local utility to examine the power quality being supplied.